Great. Thank you for the invitation to be here. I'm excited to speak to you all today. So this work is collaborative work. All of the issues and mistakes you see are my own, but the ideas in this project are generated in conjunction with my team at the UNC Causal Inference Research Laboratory and friends, some of whom are shown here. The premise of this talk is that the people we work with make public health decisions at many levels all over the world, but the resources to collect epidemiologic data are finite and likely neither optimally or equitably distributed. And so the ability to address important public health questions with mismeasured, incomplete, and partial data is critical. And so that's the motivation behind the talk I'm giving today, where we'll focus on mismeasured outcomes. The big picture here reflects a few themes you'll see running through this talk and my work in general. The first is that today we're really focused on estimating risk functions as something that adds more richness than thinking about risk at a single time point, or even worse, just reporting comparisons of single time point risk with no context. Today I'll be focusing on single samples. This might seem an odd choice for a causal talk, but when we reflect on the identification assumptions we need for causal inference, one that often goes unstated is that we must assume that our outcomes, exposures, and covariates are measured without error. Here I'll be focusing on the assumption that the outcomes are measured without error. And we can gain a lot of simplicity by looking at one sample at a time. Of course, that doesn't mean we aren't thinking about one sample under some counterfactual exposure distribution, and I will touch on that a bit in this talk. The third theme is that I'll be using external information. This is something that can be somewhat contentious, and I think the argument about this ends up being a bit misguided, because we're always using external information in our studies. We use external information to decide what to study, and we use external information to decide to what extent we think our assumptions are met. Specifically, we often assume that our outcomes are measured perfectly, which is something that is guided by our knowledge outside the study. Fourth, I'll be really focused on properly accounting for uncertainty in this talk. And then fifth, to bring us full circle, is I want to focus on answering the question we set out to ask, rather than changing or adapting the question to suit our data or an estimator. So look for these themes to crop up throughout this talk. This talk is in two parts. The first bit will focus on misclassification of event types, and the second will focus on measurement error in event times. So I am a visual learner and explainer, so I'll be using line diagrams like this to describe some of these problems. This line diagram shows three different types of outcomes. There's the dot outcome, which is one outcome type. There's the diamond outcome, which is a competing event for the dot outcome. And then people with these arrows are right-censored. In the first part of this talk, I'll be focusing on the situation where some dots are misclassified as diamonds and vice versa. So in this part of the talk, we assume that the event times themselves are correct, but that the event types are measured with error. I'll use this motivating example where we're really interested in estimating the risk of loss to follow-up and death prior to loss to follow-up in East Africa. And I'll come back to the example in depth later, but here I'll just say that the goals were to estimate the risk of death and disengagement from care, accounting for misclassification of some deaths as loss to follow-up and vice versa. And if you don't work in this area, this might sound a bit strange, but it is in settings without vital statistics registries, it can be difficult to know if someone dies. And so often in East Africa, people seeking care for HIV were being classified as lost to follow-up when they stopped coming back, when really the reason they had stopped coming back was because they had died. And so in this setting, this misclassification is not uncommon. And so in addition to accounting for that misclassification, we wanted to compute honest confidence intervals that account for uncertainty in this in our understanding of the measurement of event type. The parameter of interest here was the risk, or the probability that the event time was less than t and that the event type was either death or disengagement from care. And I'll be calling those F1 and F2. And we need the J here because there are two event types. As I said, death is a competing event for loss to follow-up, and loss to follow-up is a competing event for death prior to loss to follow-up. Where here J equals 1 signifies death prior to loss to follow-up, and J equals 2 signifies loss to follow-up prior to death. The standard estimator we might use here is the Ayla-Johansen estimator, which is the cause-specific hazard scaled by the overall survival function summed over time. And the standard approach would be to fit this estimator to the observed event times and event types in the data. So I'm calling that guy F star of J. Which is fine, and this estimator will be consistent if there's no misclassification of event type. However, if we think this misclassification is happening, we need to adapt this estimator to account for the misclassification. And so this is the estimator we propose in the 2019 paper. I will show you the citation. I think it's on the next slide, where we have our corrected estimator here, the estimator accounting for the misclassification, is a function of the observed cumulative probability of the observed event type 1 and the cumulative probability of observed event type 2, all scaled by this function of A and B, where A and B are the complements of sensitivity and specificity. So A is the probability of being observed to be event type 2, given that you had event type 1, and B is the probability of being observed to be event type 1, given that you really had event type 2. And so, this is the estimator if we assume that the misclassification is non-differential. We also expanded this estimator to account for differential misclassification, where you actually have to take apart this Ayla-Johansen estimator and the cause-specific cumulative hazard function, where I started to write this out on the slide, but it's not complicated, it's just quite long. So I'm referring you to the paper to look into that, but it's not difficult to allow this estimator to vary by whatever covariate you like, including time. So if you wanted sensitivity and specificity to be a function of time, that's pretty straightforward. Now, this exercise got me thinking about what it means if you're in a single sample where we haven't imposed any interventions. What does it mean to allow outcome misclassification to be differential over time? And so a bunch of us got thinking about this and wrote this paper in Epidemiology looking at how differential outcome misclassification matters or doesn't for estimating. We just use prevalence here to avoid the deal with the whole risk function. And what we found is it really, the extent to which differential outcome misclassification matters in a single sample problem depends on where you're getting your information about A and B, or sensitivity and specificity. Namely, if the information about sensitivity and specificity comes from your target population, it doesn't matter if it's differential or not, because you've appropriately averaged over the distribution of people in your target population. But if your information about sensitivity and specificity come from a different population with a different distribution of covariates that predicts the outcome, and your outcome measurement is differential by those things, then in fact you do need to allow sensitivity and specificity to be differential. And so this took us down a rabbit hole, which I think was useful and actually reassured me that in most cases, if your estimates of A and B here come from the population of interest, you in fact can often disregard differential misclassification in settings where you're just interested in that single sample parameter in your target population. So that was part of my rationale for not showing you the big long estimator on the last slide. Okay, but this is really the crux of the issue. Where do we get information on A and B, or sensitivity and specificity? ideally, although I guess this ideally could be up for debate, in my mind, ideally, you would have validation data collected from the target population. However, if validation data are not available, there are alternatives to this, including synthesizing expert knowledge, which I'm putting in quotes, into a distribution around A and B, or performing sensitivity analysis where you vary A and B across a range of plausible values. And any of these will provide you an answer that is only as good as your estimates of A. And so here, let's focus first on the setting where we have validation data and just focus on this bottom part for this first explanation, where we have the main study on the left and the validation data on the right. And in the validation data, we have measurements for both the potentially mismeasured outcome and the true outcome indicator. And we can use the validation data to compute the probabilities A and B, or the probability of being misclassified in either direction. And the validation data need not have information on the times unless you think that the A and B are varying over time. When we go to perform the analysis and compute 95% confidence intervals or standard errors, we have proposed this double bootstrapping approach, where rather than simply bootstrapping the main study data and applying the correction, we bootstrap both the main study data and the validation data in each iteration. And then in each bootstrap iteration, I'm showing you here 4, we would usually do, 2000. In each bootstrap iteration, we're resampling both the main study data and the validation data. And doing that allows the uncertainty in the estimation of A and B to propagate through the analysis into our final 95% confidence interval, giving us appropriate coverage. And I'll show you some simulation results in a couple of slides that illustrate this. Oh, in one slide. And so here's results from a simulation study we did to examine this property, where here the solid line, this is the naive estimator that does not account for misclassification. The dotted line, this is an estimator that accounts for misclassification, but assumes that A and B are known, estimates them once from a validation study, and doesn't account for any variability in those values. And the dotted line here, this is our proposed estimator with this double bootstrapping approach. And you can see that as the size of the validation study increases, our estimator becomes more precise, as you would expect. Whereas if we assume sensitivity and specificity are known, the estimated standard errors remain constant over time, as they do with the naive estimator. And building off this, the 95% confidence interval coverage reflects these trends, where coverage is very poor for the naive estimator because it's biased. Coverage is actually very poor for the estimator that corrects for misclassification but ignores the uncertainty in A and B, especially at small validation sample sizes. But our proposed estimator has pretty good coverage throughout. And so this is the purpose of this double bootstrapping, and properly propagating the uncertainty we have in A and B. So remember, I talked about an example early on where we have just under 4,000 participants in an HIV care and treatment program followed from entry into care for 1 year. They're about 34% male, and the mean age at enrollment was 34 years. That wasn't on purpose to get doubling 34s there. And when we looked at just the observed data, it appeared that 67 had died and 874 had appeared lost to follow-up. And after discussing extensively with people involved in the collection of the data, they were pretty confident there were no false positive deaths. So we felt confident that B would be 0. But an external tracing study was conducted among a separate group of about 4,000 people who appeared to be disengaged from care in the same area. And overall, among that group of 4,000, 77% of the deaths that actually occurred were recorded in the data as losses to follow-up, implying that A here equals 0.77 and B equals 0. And so when we applied these values of A and B to our proposed estimator, we see these results, where the cumulative incidence of mortality prior to loss to follow-up actually changed substantially after applying this approach. And you can see the confidence intervals are much wider because we did the exercise of resampling the validation data as well. And we also see that the cumulative incidence of disengagement from care that we estimate using this proposed approach was slightly lower, and again, confidence intervals were wider. So this would have dramatically altered our conclusions about mortality and loss of follow-up in this population. When we ask a causal question, the parameter moves away from the observed risk to this potential or counterfactual risk function. I am probably preaching to the choir for this group, but we all know that under appropriate identification conditions, we can estimate these counterfactual risks using inverse probability weighting or G computation. Here we looked at a setting where we weighted the Aylan-Johansson estimator that we described earlier to obtain these counterfactual risks. Of course, if the outcome is subject to misclassification, these counterfactual risks will not, we won't be able to estimate them well because we have outcome measurement error. And so in that setting, we can use a similar estimator to what we described above, where our estimator that corrects from this classification is a function of the estimated counterfactual risk using the observed outcome indicator and these functions A and B. Now things get more interesting if we think that misclassification might be differential. If we think misclassification might be differential by A, we can account for that easily by simply letting A of, oh, this is a terrible abuse of notation here. I've used A as both the treatment and my misclassification parameter. Sorry about that. If we let the misclassification parameters A and B vary by values of treatment, we simply create parallel versions of this estimator, one for treatment equals 1 and one for treatment equals 0. However, if we think that the values of the misclassification parameters A and B vary by covariates or time, we will have to do what we did in the single sample setting where we deconstruct the estimator for the cumulative hazard and let those values use covariate and time specific values of A and B in that function. And so this is a setting where differential misclassification may actually matter regardless of the sources of A and B because we're stratifying our curve by treatment at the end of the day. And so we did some simulations here as well. To orient you to this slide, here we have two settings. The left, we have no misclassification, and on the right, we have a setting with non-differential misclassification. And we have 5 estimators. The blue is the full data, so what we wouldn't usually get to see, but we can see here. The green uses the misclassified outcome measure and assumes it's the truth. The yellow accounts for misclassification, but assumes that it's non-differential. The red assumes misclassification is differential by A, and the purple assumes it's differential by both A and T. And you can see when there's no misclassification, they all work great. When there is non-differential misclassification on the right, all of the estimators that account for misclassification work fine, but the naive approach has some bias, which is what we would expect. And the more flexible we are over here, by allowing misclassification to be differential by more thing, the wider the variability is around the bias. And when we look now at simulations under differential misclassification, here by A and here by T, we see something interesting, which is why I wanted to highlight this. We see the naive approach is still biased, but more importantly, the approach that accounts for misclassification but assumes that it's non-differential has more bias than not accounting for the misclassification at all. And this was an important caution for me, because we often think, like, if we have validation data that doesn't have exposure measured, well, it's better than doing nothing to account for the misclassification and assume it's non-differential, but that might not be the case. However, in this scenario, if we let misclassification vary by A or A and T, we did just fine. And in this last setting where misclassification was differential by time, you see a similar pattern where we see some bias if you don't use the appropriate amount of flexibility, but if we use this purple estimator, which is differential by A and T, we get back an unbiased result. Okay, this is the end of part 1. So we've shown a simple approach to account for misclassification in cumulative incidence functions if the event time is known, but the type is subject to error. Of course, this requires additional information, hopefully in the form of validation data, if not expert opinion. And we showed some extensions to a causal setting. I love this phrase "are straightforward." I feel like this is something that methodologists use all the time, and it is infuriating as a listener if you don't find it straightforward. That wasn't my intention here. Perhaps I should have said are possible. Okay, I'm going to take a breath for 1 moment before I start part 2. All right, we're back to the line diagram to begin part 2. This is a line diagram here where these bars represent events and the arrows at the end represent censoring. And in this setting, we're assuming that the black lines are the truth. We might have several different types of measurement error where our observed data might take the form of these red lines. So for example, this first line, I can advance my slides. For this first person, their event time was measured accurately, and they were accurately recorded as an event at that time. The second event was detected late. The third event was missed entirely. The fourth event was appropriately counted as censoring at the end of follow-up, or sorry, the fourth record. The fifth record was a false positive event. They truly didn't have the event and were censored, but they appeared as an event in the data early. And the fourth person was an event detected early. And so really, this is a false positive event that happened prior to a true event. So these are the types of outcome misclassification we have when the event times are subject to error as well. For simplicity, in this part of the talk, I'm assuming we just have 1 event type rather than 2. I'll use an example for this part of the talk from the Pfizer COVID vaccine trial study. And this is a figure from their New England Journal paper on the right. Of course, we did not have access to these data, but we did have access to the published risk functions and the FDA report that had the number of events and censored by week. And so following methods from this paper referenced down here, we use those counts to reconstruct the risk under no vaccine for this example. I'll just be focusing on this blue line here. So in this example, all 3 types of outcome misclassification are plausible, even if not probable. By the way, I think I want to just say up front, I think the study was very, very nicely done, and this is not meant to be a critique of their of the New England Journal paper at all. This is just a what-if exercise. We want to know what would the true risk be under various hypotheses about the probability of each type of outcome measurement error, specifically false positive events, imperfect sensitivity, and delayed event detection. So the notation here, which is recycled, is that the T is the true time to event and W is the observed time to event. And we're proposing this estimator where the cumulative incidence of the true event times is a function of the cumulative incidence using the observed event times and A and B, where here, again, A and B are recycled. These are not the same A and B that we saw last time. Where here A is the probability of having an observed event, is observing your event before time t, given that your true event happened before time t. And B is the probability that your observed event happened before time t, given that your true event happened after time t. And so these are hard things to think about, A and B. They're these weird cumulative functions over time. And so where can we get information on these? Well, ideally, we would have this great auxiliary or validation data source. We can talk more about that if we have time, but often in this setting, if you had rich enough auxiliary data, you could just do your study in that data set and you wouldn't need these methods at all. There are also settings where you don't have auxiliary data, but you have some external knowledge about distributions around the components of A and B, and I'll talk about those in a moment. Or we could do some sort of quantitative bias analysis where you look at, well, how would the cumulative incidence or the risk function have changed under various assumptions about these things? But even if we're using expert knowledge or doing a quantitative bias analysis, how do we specify these kind of complicated functions? Without rich validation data, we can't estimate them, but we can look at what they might look like under various assumptions about quantities we might have intuition about. And so I'll use a toy line diagram to illustrate this. So we'll consider B first. And here we have a line diagram from time 0 to t. And because B is conditional on having the event after t, we'll show the t out here. This is big T, this is a true time to the event. And the question is the cumulative probability of W up until time t. And framed like this, one option is to assume that the false positive rate is constant over time and use the exponential formula to specify B just like this. And there should be a negative sign here. Sorry, that fell out in my attempt to make this whiteboard-like. So this is 1 minus e to the negative false positive rate times time. And so B is pretty straightforward. We can specify this function B by only specifying the false positive rate if we assume that the false positive rate is constant over time. A is a little bit trickier because when we're thinking about A, the true time to the event has happened in between time 0 and the time t where we're thinking. And so A really has 3 components. It has, what is the probability that W happened before t, given that t is in this window? What's the probability that W and T are equal? And what's the probability that, given neither of those other things happened, we see W after T, but before, after the true event time, but before the time that we're interested in, little t. And so we can take these one at a time. This first probability, this is the probability that we saw W inappropriately early. So we can think about this as a false positive event. And the issue here is that we don't actually know, I'm calling this quantity Y, we don't actually know when T happened for any one person, because if we did, we wouldn't have to do this study. And so this will seem a bit hand-wavy, but to get around this, I simply integrated this probability over time and substituted in evaluating the integral using our false positive rate that we described when we talked about B. So this is the same false positive rate we used earlier, just for this quantity, the probability that W is less than T. Next, we can think about the probability that W equals T, or that we observed the event right when it happened, given that you hadn't been a false positive previously. This is a familiar notion of sensitivity. I think we have decent intuition about this, and you can think about if your event was detected using a repeated test, this would just be the sensitivity of that test. And so this is a quantity I'll just leave as a probability, and we can think about various sources of external knowledge for that. And then the third component is this component C, which is the probability that W was less than little t, given that it was greater than the true time to the event. And so what this implies is that there's some sort of delayed event detection after the true event. And I'll think about this in terms of an event detection rate after the true event. So given that you weren't a false positive, and given that you had not, you did not have your event detected right when it happened, what is the rate of detection after that? And because we don't actually observe the true t for anyone here, this is another situation where we're simply integrating over the possibility that t happens anytime in this range. And we can simplify this down by evaluating that integral down to the a function of the, what I'm calling the true positive rate, of the event detection rate in time. And so we have these three quantities. We have these components, y, which is the probability of having the false positive prior to t, the sensitivity, which is the probability of observing you at your true event time, and the probability of an delayed event detection between your true event time and the time point of interest. And putting those together, we can develop this expression for A, which that was a lot of words, and there are a lot of less than and greater than symbols on this slide. But what it comes down to is that we can compute approximate values of A and B using knowledge about reasonable values for just three quantities: the false positive rate, the probability of being identified correctly as an event at the event time, which we'll call sensitivity, and the event detection rate after an event. And so, these Y and C are really approximations, because to evaluate the integral I showed you, we had to make this assumption that there is a constant true event rate up until time t. We don't impose that assumption on our final risk function. We just use it to get y and t. So one thing I was interested in exploring in simulations is how well these approximations performed if the true time to the event distribution was not exponential. We were in settings with increasing or decreasing hazard functions. And so we performed a set of simulations where we had 4,000 people. The true time to the event followed a variable distribution such that the true risk at 2 years was 20%. And we started with an increasing hazard over time. I call this alpha equals 2, but I realized people parameterize the Weibull distribution very differently depending on where you are. So I'll just tell you that alpha equals 2 in my notation implies an increasing hazard function. And the observed time to the event distribution was generated under various scenarios. So with sensitivity equal to 0 and 70%, the event detection rate equal to 0 and 0.18, and the false positive rate equal to 0 and 0.05. And when we did that, we computed risk functions using the estimator I've described and using the estimator that ignores the misclassification, which I'm calling the naive. And I evaluated the risk function at, I think this is 8 time points, and plotted them here using box plots. And so this first figure on the left, there's perfect sensitivity and no false positives. And so as expected, both approaches fall right along this line, which represents the truth. The black line is the true risk function. When sensitivity is imperfect, you see that the naive approach, as you would expect, it underestimates the true risk function, but our approach gets it back pretty closely throughout follow-up. Here in this next column, we've said, okay, sensitivity was still only 70%, but now there's some delayed event detection. And so, the naive does slightly better because it's catching up. However, our proposed estimator has very little bias in all of these time points we've looked at. And then this bottom row is the same set of scenarios, except now we've added some false positives. And actually, when the event is rare, even a very low false positive rate can have a dramatic impact. You see it switches now the bias is in an upward direction, whereas in the top row, the bias is in a downward direction for the naive estimator. But regardless, our proposed approach works well to handle these, 3 different types of outcome misclassification. And so one thing I was wondering is, okay, well, here we specified an increasing hazard function over time. We're relying on this approximation. What if the hazard was even less constant over time, so increasing even more dramatically? So I repeated this exercise for a variety of hazard function shapes. Here I'm showing you one where we're back to the Weibull distribution, but alpha equals 4 rather than 2. So this is like a very dramatically increasing hazard, as you can see by the shape of this risk function. It's pretty much flat at the beginning and then starts to take off. And the results are pretty similar. the naive approach still has bias in the same directions as before, and our proposed approach still works pretty well at all of the times examined. And so we have a whole slate of these looking at different shapes of the hazard function. I have yet to break our approach beyond, the third decimal place in terms of bias, although I'm continuing to investigate this to kind of push it to its limits and see, hopefully develop some sort of guidance about when these approximations are appropriate and when you might want to be careful. So to return quickly to our example, remember, these are the sort of mimicked data from the control group of the COVID-19 vaccine trial by Pfizer. Here's the risk function that I generated. You can see it's much more stair-steppy than the original because we had to do this imputation of the exact event times based on the weeks. But it gets you to the same place, a true risk of about, or an observed risk of just over 2% at the end of follow-up. And using this risk function and the methods I described, we can ask questions about the risk function. For example, what if there were no false positives, but sensitivity was only 80%? And that would yield this red risk function here, which you can see ends at, just over 2.5%. Or we can ask questions like, what if sensitivity was 80% and there was a rate of event detection after if you had missed the event? And so you can see that this red line representing this scenario is a little bit closer to the observed than the previous estimated line. And then finally, we could say, okay, well, what if we think there are some false positives? So we think that, even had no one had the event, just with the tests that we know they were using, 0.5% would have appeared to be a false positive by the end of the study. We can take that, turn that into a rate, and we would have gotten this red line. Here, where I've grayed out the previous two scenarios so you can see how they're changing. And this function at the bottom is the function that corresponds to the scenario described here. And so that's all well and good. We could do this all day. We could come up with various stories. It's difficult to converge to the answer, which is what decision makers often want if we're just doing these one-off what if exercises. And so there are two suggestions I have here when we're thinking about this. The first is to create what I'm calling bounds on plausible values. So think best case scenario, what do we think sensitivity, or what do we think the values of sensitivity, the false positive rate, and the event detection rate would be? And worst case scenario, what would they be? And then use those to get bounds on the risk. Of course, they're not real bounds, right? We often think about bounds as logical bounds, like it would be impossible for the risk to be above this value. But when we're talking about outcome misclassification, the logical bounds are 0 and 1. But the bounds of the plausible values might be much narrower. So for example, what if we think that the values of the parameters that would correspond to the lowest possible risk would be to say, okay, we think there are a lot of false positives, about 0.5% by the end of the study, which translates to this false positive rate. And we think sensitivity is perfect in the study. So essentially, we think we've seen all the events there are, and actually some extra ones, so we should revise the estimate really far down. And then the upper sort of plausible bound, we might say, is that we think, okay, there are no false positives, and we've only detected half of the events, and there's no delayed event detection. So this is one strategy, and we can plot those alongside the observed data, which would look something like this. And this could help us rule out certain areas of this plot, right? Under these plausible bounds we specified, we might say, we really don't think the true risk is below 1.5% or above 4%, for example. Alternatively, we can turn to Monte Carlo sensitivity analysis, where we draw the measurement parameters from a distribution around their most likely values based on expert opinion or our own understanding of the situation, and repeat this many times. And so, for example, here we went through this exercise where we drew sensitivity from a beta distribution centered at 80%. And then we drew the probability of being a false positive by the end of the study and the probability of detecting an event by 30 days after its true event time. We drew those probabilities from beta distributions as well, and then converted them back to their corresponding rates and repeated this. And then we plugged those values into the estimator and repeated this all 10,000 times. And so this gave us a distribution of risk functions, which I've plotted here in like very, very transparent ink. So when they're on top of each other, you can see them. When they're not, they're pretty much invisible. And just to give you a sense of the range, and then I plotted the median in purple on top of that. And so this gives you a sense of, for these plausible values, what is the range of compatible estimates? If we were to want to compute confidence intervals on top of this, we could turn to the methods we used in the first part of the talk, where we did this double bootstrap approach, where the main study data were resampled at each iteration, and we drew from these distributions at each iteration, and the corresponding range at the end would be our distribution of our final risk at each time point, which we could use to create 95% confidence intervals. Here, I did not go that final step because these are reconstructed data, although we could. So, all right, I'm going to wrap up to try to leave time for questions. To summarize the second part of the talk, outcome misclassification is different and more complicated when outcome times are taken into account, particularly when we have right sensory. While the estimator I showed you itself is simple, just a proportion and some arithmetic, the misclassification parameter inputs are now functions rather than single numbers, which honestly is too many dimensions to think about in terms of a sensitivity analysis. And so to move forward, it requires some simplifications on our parts. Like we assumed that the false positive event rate was constant. We assumed that the event detection rate was constant over time. And even so, we had to do these approximations that I described earlier. And we could make all of this more complicated than that. There's no reason we have to assume that the false positive event rate is constant over time. For example, we could specify some Weibull distribution for the false positive event rate, but the probability of having the detailed knowledge we would need to do that is low. So this is a setting where all of the pieces can be made, more complex until you let them be non-parametric. However, having the data to specify those pieces would be very difficult. If you have a large validation data set, it offers a way forward to be even more flexible. But these are only available in some settings. I can think of a few settings where EHR data might be available to validate the outcome times or something, or some other big data source. But small validation data sets here are problematic because they don't provide the resolution you need to get these functions over time. Okay, to wrap up, outcome misclassification is common, and we often ignore it. Even worse than ignoring the outcome misclassification is it's often used as a reason not to do a study, which I'm not lobbying for doing studies and getting the wrong answer, but when we choose not to do a study, that has consequences for public health. And we try to make evidence-based decisions, but in settings with no evidence, we're making a default decision that may not be optimal. To make progress, we need approaches to make inference even when outcome measurement is prone to error. So we've shown 2 of those. These are not the only 2. And hopefully these could be added to a toolkit, not meant to supplant existing approaches. And the estimators I've described are simple in and of themselves, but the theme here is that obtaining the knowledge needed to parameterize them can be complex in settings with or without validation data and requires thought. This is often not a step we plan into our studies because it's difficult, and we like to think that our outcome measurement will be perfect. But in settings where we know that the outcome measurement is subject to error, perhaps we should be spending more time as a field thinking about how to obtain the knowledge we need to parameterize these methods to account for outcome measurement error. Even if we have detailed validation data, challenges remain. I want to point these out just as a caution because I don't want to sound like I'm saying that validation data are panacea. small validation data sets here are pretty unstable when you need things estimated over time. Excuse me. And of course, validation data themselves may not collect the gold standard that you're interested in. So just a meta comment to keep in mind that the validation data themselves might be subject to error. So I don't want to end on that sort of depressing note. I think that reflecting on methods to account for outcome measurement error gives us opportunities to use data sources we wouldn't otherwise be able to use for epidemiology, and to start to use data that might not have been collected for research purposes to learn about public health, which will benefit everyone and move us forward as a field. So I'm going to stop there. I hope I saved a few minutes for questions, and I'm happy to discuss more.